In the last video, we saw an application of the Euclidean algorithm, and now, and it was kind of worked here. Notice that if you print out the slides, I did make a little typo here. So we found that the GCD of 31, 56, and 22 was 2. Okay. So now, what could be kind of interesting to think about and work with is to see if we get something interesting when we work this algorithm backwards. So in essence, if the algorithm was used to find the GCD of the two numbers, but now if we know the GCD, can we say something from the two numbers? Or about the two numbers. So we want to take the GCD and then use it to find some information about A and B. Okay, so we might think, well, start backwards, work with the last line. Then there isn't really that much to work with. Okay, so I'm not going to work with this. Now, going forward, what do I need to pay attention to? So I'm going to start with this second to last line. I need to pay attention to the GCD, which is 2, and I also need to pay attention to any instances where I have my remainders or quotients, my remainders or the two numbers I started with. Okay, so 31, 56, and 22 were the two numbers I started with, and 10 ended up being one of the remainders. Okay, so now kind of what I'm going to do is start with that second to last line. Okay, that's fine. 22 is equal to 2 times 10 plus 2. Okay, true statement. Now, I kind of want to isolate the 2. So I'm going to, again, write 22 minus, and then 2 times 10 is equal to 2. Okay, I've isolated the GCD, and now I just need to manipulate this. So 22 is already one of the two numbers I started with. Now I need to change the 10 into something else. Okay, so remember 10 was one of my remainders, and I want to change 10, so I involve this 3156. That is to say, one way I could do that is make a substitution where this first equation is isolated for 10. So 10 is equal to 3156 minus 143 times 22. Okay, and if I make that substitution in here, I get this statement, minus 143 times 22 is equal to 2. And now with this, I can just rearrange this a little bit. Okay, so distribute the 2, and I would get minus 2 times, and I'm going to leave it in this kind of factored form, 2 times 3156, and then plus, I'd have 2 times 143 is 286, and then if I add the other 22 that's hanging outside, that would be 287 times 22 is equal to 2. Okay, so this is telling me if I were to take my calculator and do negative 2 times 3156 plus 287 times 22, I should get 2, and it does check. I made sure. But what this is kind of looking like is that there is a constant. There's a constant here, kind of a U letter, because this is A. Okay, that's an A that we started with, and B was over here, another number that we started with, and this we might call V, and then over here is our GCD. Okay, so in essence, what this is saying is that the GCD can be expressed as a linear combination of A and B that we started with. That's kind of cool. And so working the Euclidean algorithm backwards leads to the extended Euclidean algorithm. Okay, and here's the formal statement. Okay, more or less what we just said above. The only thing that it adds on it is that if we know one solution, U and V, we can get every other solution by doing these formulas. Okay, and I'm not going to go through the proof because the proof is rather short in the text and it's fairly straightforward, so make sure to have a look at that. One last idea from this section is that when we talk about greatest common divisors and everything, there's this idea that if we're given two numbers, we can say that the two numbers are relatively prime. And what this means is that these two numbers are going to be relatively prime if the GCD of the two numbers is 1. Okay, and you may have run across this language before, maybe not, but just going to introduce it for the sake. And all I can say right now is that we do use this concept of relatively prime over and over and over in cryptography, and in fact we like it if the numbers are prime to begin with, but in the event that they are not prime, we at least like them to be relatively prime. So there's a lot of stuff that we're going to see this semester that does incorporate this idea of relatively prime. And apart from that, that's kind of the end of the Euclidean algorithm and divisibility ideas that we'll see in this video.